Today, we're taking a rapid-fire journey to demystify the ultimate rules of reality. Yep, we're talking about physics, and more specifically, the laws of motion. So grab a coffee, get focused, and let's just dive right in. Okay, let me ask you something. Are you at rest, or are you in motion right now? You might think you're just sitting there perfectly still, but this one simple question, it totally changes how we view the entire universe.
Which brings us to Section 1. Rest and motion are relative.
Imagine you're sitting on a train, just chatting with a friend. To that friend sitting right across from you, you're completely at rest, right? You aren't moving relative to them. But to someone standing outside in a field watching that train go by, you are zooming past them at high speed. Let's take it even further. If you're sitting perfectly still in your room right now, you feel like you're at rest. But to an alien observing Earth from Mars, you are currently spinning and hurtling through the solar system at literally thousands of miles per hour. So whether you're moving or not, well, it strictly depends on who's watching.
Now, to understand all of this, we've got to set up our physics toolkit. And in physics, we deal strictly with physical quantities. These are things we can actually assign a number to and measure, like the distance you walked, the time it took, or the physical force of a push. What we don't measure are subjective things, like human emotions or the pain of getting slapped. Sure, those are very real experiences, but they aren't physical quantities because we can't objectively put them on a scale.
Moving right along to Section 2, Scalar versus Vector Quantities. Now, what's really interesting here is how we split these measurable quantities into two distinct kinds of twins. First up, the scalar quantity. A scalar only cares about magnitude, which, by the way, is just a fancy word for the numerical amount. For example, if you sit down and eat 2 kilograms of sweets, well, first of all, that's a lot of sweets, but it doesn't matter which direction you ate them from. You simply consume 2 kilos. It's just simple addition. But then we have the vector quantity. A vector needs a magnitude plus a specific direction. So if you say you're applying 10 newtons of physical force, that just isn't enough information. We have to know where exactly that force is pointing.
Think back to a playground tug-of-war. If two of your friends pull on your arms with 10 newtons of force, but in completely opposite directions, what happens? Nothing. They cancel each other out and you stay totally still. But if both of those friends pull you with 10 newtons of force in the exact same direction, suddenly you've got 20 newtons of force pulling you, and boom, you move. The numbers were exactly the same in both scenarios, but the direction completely changed the final outcome. And that, right there, is the power of a vector.
All right, Section 3, Distance versus Displacement.
Let's look at probably the most famous pair of physics twins and bust the myth that they're the same thing. Imagine a girl, let's call her Champa, doing a moonwalk across her living room. She starts out, dances straight forward, and suddenly her dad walks in and catches her. Totally embarrassed, she stops dead in her tracks, turns around, and moonwalks straight back to where she started. Now the total path she covered, every single step forward plus all those steps backward, that represents her distance.
So distance tracks every single step of your journey. And because it doesn't care at all about the direction you were facing, only how much ground you covered overall, distance is a scalar quantity. It's always a positive number. Displacement, on the other hand, that's a vector. Displacement only cares about the shortest straight line gap between where you started and where you finally ended up. If Champa started in the center of the room and finished in the center of the room, her displacement is completely zero, even if her total distance was like 20 steps.
Let's apply this to a classic textbook puzzle. A farmer is walking around a square field, and every side of this field is exactly 10 meters long. One full round takes him 40 seconds. So at 140 seconds, he's walked exactly 3.5 rounds. Since distance is just the total path, his distance is simply 140 meters. Easy, right? Just addition. But what about his displacement? After 3.5 rounds, he ends up exactly at the diagonally opposite corner from where he started. To find that shortest path, we actually have to use vector addition. Specifically, we use the Pythagorean theorem to find the length of that diagonal across the field. And that gives us a displacement of 10 root 2 meters. Completely different numbers from the exact same walk.
Okay, let's add time into the mix with Section 4, Speed versus Velocity. So speed pairs directly with distance. It's like a package deal. To find your speed, you just divide distance by time. And just like distance, speed is a scalar quantity. If you're driving at 50 miles per hour, that's your speed. It doesn't require a direction. Velocity, though, pairs with displacement. To find it, you divide displacement by time. And since displacement is a vector, velocity is also a vector. It absolutely demands a direction. Saying you're driving 50 miles per hour east, now that is a velocity.
Oh, and here is a massive shortcut for you. You're going to want to remember the fraction 5/18. When you're calculating speed and velocity, you constantly have to convert between kilometers per hour and meters per second. And honestly, doing the long math, multiplying by 1,000, dividing by 3,600, it takes forever. Instead, if you have a speed in kilometers per hour, just multiply it by 5/18 to instantly get meters per second. Seriously, commit that to memory. Absolute game changer.
Which leads us perfectly into Section 5, Calculating Averages and Conversions.
The key here is just identifying the right mathematical trick for whatever scenario you're looking at. The standard way to find an average speed is simple: total distance divided by total time. But if a problem tells you a journey is split into two parts where the distances are exactly equal, like say you drove 50 miles there and 50 miles back, but at different speeds, you can use a slick shortcut. Just plug it into the formula: 2 times velocity 1 times velocity 2, all divided by velocity 1 plus velocity 2. On the flip side, if you traveled for two equal blocks of time at different speeds, you literally just add the two speeds together and divide by 2. Using these specific tricks means you won't get bogged down in long, messy algebra.
And finally, Section 6, the basics of acceleration.
Let's look at the final piece of our motion puzzle. Anytime your velocity changes over time, you are dealing with acceleration. Now, think back to our definition of velocity. It has both magnitude, meaning speed, and direction, which means you can actually accelerate in two totally different ways. First, by changing your speed, like, revving a bike to go faster and look cool for a crowd, or slamming on the brakes. But second, you can accelerate simply by changing your direction. Even if your speed stays exactly the same, the very second you turn the handlebars of that bike to go around a curve, your direction changes. And because your direction changes, your velocity changes, which means you are technically accelerating. Mind-blowing, right?
To wrap up this explainer, I want to leave you with one final thought from our source material that really struck a chord with me. Quote, "The time that passes never comes back. Trust yourself, keep working hard, and you will beat everyone." Look, you are not a static object. You literally have the power to control your own velocity in life. Time is ticking, so don't stay at rest. In a universe where absolutely nothing is truly standing still, what direction are you accelerating towards? Thank you so much for joining me for this explainer, and I'll catch you in the next one.